another video with Joe and Jahan. This is Project 2 for Physics 357. Today we're going to be talking about an Arduino project that's set out to measure how pressure decays with height. The derivation is shown here. We start off by looking at a differential change in pressure due to the mass of a layer of air. And our conclusion was that pressure should decay exponentially with the height. So here's a picture of us testing out the pressure sensor writing data to the SD card using a breadboard. This was a bit tricky to set up, but it was simple to use once we had found the right libraries.
Here we have the housing for the Arduino project. It is comprised of two parts, a base and a lid. The main body of the base has a square region for the Arduino, as well as an offshoot for the 9-volt battery. On the sides are two handles to attach to our backpack, as well as vent holes to equalize the pressure inside and out. It also aids in connection between the GPS and the satellites. The lid is made so an LCD screen can fit inside, allowing for constant visualization of our data. With the beauty of Fusion 360, we can see the entire process in action. So the base is made with the housing for the Arduino and the battery. Holes are made to attach the lid to the base. Volume is reduced so that the print doesn't take as long and waste as much plastic. The lid is created with the hole for the LCD, and handles are made for the backpack attachment. Then the vents, and then finally the lid is finished.
So putting it all together, here's everything in the compute harness. We added an LCD screen, and everything is wired up and soldered together to save space without the breadboard. There's the BMP sensor measuring pressure, and here's the SD card collecting our data, and this is wired up to the GPS and the LCD. Here's what it looks like when it's collecting data. When GPS data is not streaming in, the altitude reads GPS lost. When GPS data is coming in, it prints the altitude to the screen.
Here's our Arduino code. We first start off by setting up all of our components: the SD card, the BPM pressure sensor, the GPS, and the LCD screen. In the setup, we then initialize all of these, as well as check if the BPM pressure sensor is working. If it's not, we send out an error and we wait forever. Inside the void loop, we then check the GPS and see what kind of data it's getting. Since it receives data from a bunch of satellites, we don't really need it all, so we only want to get what we really want. We then start writing to the CSV. We have a nested if statement to check if the SD card is working and if we're getting the right data. If the SD card is working, we print to the data. If it's not working, then we go down here and say SD card is not inserted. If it is working, then we check, is the data what we want? If it is, then we print to the SD card as well as print to the LCD screen so that we can see it. If it's not, then we print -1s so that we can parse it out later. We also show on the LCD screen that GPS is lost. And that's our code. Down here we have methods to make it a lot cleaner, like clear screen, select one line, select two line, and then the backlight brightness. Thank you. Here we have our data analysis program. First, we clear and close everything for a consistent start. We then import the data as a CSV in the format of column vectors: latitude, longitude, altitude, date, time, and pressure. We also import some very useful physics constants. First, we find the indices of the data that are actually usable. Due to the GPS not being completely consistent, some of our data didn't actually find altitudes, so we don't want to use that. We then plot that data in blue, as you can see on the right. For this data, we then have to fit it, so we create a theory curve and use the fit function to fit that theory to our data. We then plot it in red with the other data, and as you can see, it's a good fit. The chi-square seems to agree, because we get a chi-squared of 2.9 times 10 to the negative 6, which is very small. We get an atmosphere of 1.09 times 10 to the 5th pascals, and that seems reasonable. We also get that the temperature is about 96.3, which is a little hot. We think that some of the inaccuracies in the altitude could have resulted in this. I also used a linear fit to see if that would change anything, and it seems like it didn't, because all of the data seems to agree with the previous, and that's a good sign.